Hello learners, I am Dr. Arunkumar, faculty member, School of Management, SASTRA deemed University. In this session, we are going to discuss about the multivariate technique called factor analysis and multiple regression analysis. Let us use the output taken from SPSS, and I will also demonstrate using SPSS software. SPSS, we all know, it is a statistical package for social science. So let us understand, the learning outcome of this session will be, we will be discussing about the multivariate statistical techniques, as I said earlier, and also we will try to understand the application of factor analysis. Especially, we have exploratory factor analysis and confirmatory factor analysis. But this session will be focusing on exploratory factor analysis. And also, there is one more multivariate statistical technique is there. It is called the multiple regression analysis. And we will be discussing about what are the context in business whereby we will be using these techniques. Okay. Moving further to understand the multivariate statistical analysis. Multivariate statistical analysis refers to multiple advanced statistical techniques for examining relationships among multiple variables at the same time. Researchers use multivariate procedures in studies that involve more than one dependent variable, also known as the outcome or phenomenon of interest. More than one independent variable, or also known as predictor or both. This type of analysis is described because researchers often hypothesize that a given outcome of interest is affected or influenced by more than one thing. So, in this multivariate technique, there are two different types of analysis, but there are many statistical techniques available to conduct a multivariate statistical analysis. And the most appropriate technique for a given study actually varies with the type of the study context and what kind of the key research question we have posed. Accordingly, we will choose the appropriate multivariate statistical technique. The most common multivariate technique are multiple regression analysis and factor analysis. We will be looking into detail how to apply multiple regression analysis and factor analysis and its implication towards the research. Now let's also understand what is factor analysis. Factor analysis is a data reduction technique in which researchers reduces a large number of variables to a smaller, more manageable number of factors. For example, you put 100 questions in service quality context. Do you understand this? And you cannot do the presentation of the outcome of this 100 question, results of this 100 question to your managers involved, or the whenever you do presentation before the board. You cannot use all these 100 questions and do that. In that context, what you can do here is you can employ factor analysis. The other name of factor analysis is called data reduction techniques. So what actually data reduction technique is all about? So in data reduction technique, what happens, it tries to uncover the patterns among variables and then cluster highly interrelated variables into factors. So what happens, we are able to extract manageable factors with underlying variables in specific each dimensions or factors. So that can be precisely presented in a short manner, so that we can able to have a great effective presentation. Factor analysis, we all know, has many applications, and it is very much employed in survey research, where the researcher use a technique to see if lengthy series of questions can be grouped into shorter sets, I mean the factors. So that's the introductory part of factor analysis. And let's go in detail in understanding factor analysis. So if you look at factor analysis is commonly used, and it is also called as a data reduction technique, since many number of variables are grouped into specific factors or dimensions. Because what happened mathematically here, all those variables which are seems to be highly correlated or get interrelated and try to load in a specific factor, and those variables which is not correlating repel from the respective factor and try to load in another factor. This is the mathematical thing which is happening inside factor analysis when you rotate those factors. And the factor analysis also can be employed in instrument or questionnaire or scale development, because of the fact that any poorly loaded variables can be ignored when you develop a research instrument, in the sense that a good loading above 0.5 can be considered. Any loading in factor analysis below any variable which poorly load below 0.5 can be ignored and cannot be given, because it is not so significant. So like this, we can employ factor analysis for the purpose of scale development. The assessment of the dimensionality of the set of variables also can be learned using factor analysis. So I have given the input about where, in which context factor analysis is commonly used. And in order to understand factor analysis, regardless of the purpose, factor analysis is used in the determination of small number of factors based on a particular number of interrelated quantitative variables. I was just explaining that. And unlike variables directly measured such as speed, height, weight, etc., some variables such as egoism, creativity, happiness, religiosity, comfort are not a single measurable entity, because it is a group of variables. So try to measure this latent, dimensions. So in that context, we can use factor analysis. When you look at, they are constructs that are divided, that are derived from the measurement of other directly observable variables. Moving further to understand factor analysis, we all know that constructs are usually defined as unobservable latent variable. I can give you an example of the motivation. If you look at motivation consists of many items which really motivate an employee. Motivation is not one single item. Do you understand this? So this latent construct called motivation can be determined by many measurable variables. So similarly, like love, hate, care, anxiety, worry, stress, product quality, physical aptitude, democracy, reliability, power, and so on, can be considered as a construct, and it involves many variables put together and try to determine that construct. So in this context, I think factor analysis will be able to extract these kind of constructs whereby the interrelated variable come together in order to form a factor. For example, the construct of teaching effectiveness. You know, teaching effectiveness comprises of several variables used in order to measure the teaching effectiveness. When you look at the construct called teaching effectiveness, construct may obviously a construct may consist of several dimensions, isn't it? So when a teacher has to be assessed about his teaching effectiveness, he has to the amount of knowledge, the amount of skills, the amount of examples, the amount of interactiveness with the students, the level of motivation, the resources the faculty provide in enhancing the knowledge among the students, and also the technological usage in order to discuss the particular subject in a lucid manner. All these elements put together to form a dimension called teaching effectiveness. So in that perspective, I think factor analysis will be a very useful statistical technique to extract a particular dimension called teaching effectiveness. When you look at factor analysis measures not directly observable construct by measuring several of its underlying dimensions. If you look at a construct of service quality, this construct of service quality will comprise of many factors or dimensions. For example, like in service quality, we have empathy, we have tangibility, we have accessibility, we have convenience, we have reliability. Like that, many factors put together and form a construct, and each dimension will have underlying variables which vary from one perspective of a person to the other person's perspective. So that's why we call it as it is a variable. So a group of variables put together and form a dimension. For example, convenience is a dimension. For example, if your bank, talk about a dimension called convenience in service quality, we can quote example of the bank opens 24 hours in a day, and it operates 24 hours a day, and also the bank open on Sunday also. So there are two variables involved: 24/7 operations, as well as the bank operates on Sunday. So there are two variables. Like that, many more variables put together and form a dimension called convenience. And like this dimension, there are many more dimensions put together and to form a construct called factor analysis. So the identification of such underlying dimensions simplifies the understanding and description of the complex construct. I think with this example just now I was quoting about service quality construct comprised of 5 dimensions, and each dimension will have many variables. I was quoting example of convenience. Convenience has many variables, like for example a variable A, which talks about 24/7 operating hours, and variable B, it talks about opening bank operation on Sunday too. So that's about I think with this input and example, hope you all understand the difference between a construct and the dimension or factors and the respective variables associated with that particular factor. So moving further, generally the number of factors is much smaller than the number of variables are measured. In my case, like when you look at the service quality construct developed by Parsuram, Zaithmal, and Berry. There are 22 measures, variables has been put in that particular instrument or scale, and there were 5 dimensions developed by them. As I mentioned, convenience, accessibility, reliability, tangibility, all these dimensions put together and form a construct, and there are 22 measures or variables in that instrument. Therefore, the expectations is that a factor represents a set of measures. From this angle, factor analysis is viewed as a data reduction technique because this 22 variable get minimized into only 5 factors, 5 dimensions, as in the case of the instrument developed by Parsuram, Zaithmal, and Berry in the year 1988. You can Google it, and you can look at the scale, and the scale consists of 5 dimensions and 22 variable. Just Google it and do self-learning, and it will give you a better understanding and reinforce the knowledge about factor analysis. And moving further about the factor analysis, the assumption of factor analysis is that the underlying dimensions, what we call factors, can be used to explain complex phenomena called service quality. Observed correlation between variables result from their sharing of factors. In my case of this example, what I have given you, that measures like operating 24 hours, 24/7, and opening on Sunday, these 2 variables join together and form a factor called convenience. So that's what it mentioned here. Observed correlation between variables result from the sharing of factors. Clear? So see, if you look at the application of factor analysis, this session will also examine 3 common applications of factor analysis. One is defining indicators of the respective construct, and also the next one is defining dimensions for an existing measure, and also selecting items or scales to be included in a measure. I think we will be looking into detail to make you understand, give you fundamental clarity on the concept called factor analysis. So the application of factor analysis, let's talk about the defining indicators of the construct. So ideally, 4 or more measures should be chosen to represent each construct of interest, in the sense that there are many more variables form dimensions, and dimensions form a construct. The choice of measures should, as much as possible, be guided by definitely a theory about service quality, and also we can try to take the measures or variables by reviewing the past literature, and whatever the variables we have taken can be employed, as well as any variable that is a lacuna or research gap that can be fulfilled by substituting and extracting the variable by synthesizing the literature review, and we try to connect logic among these dimensions, variables, and the construct. And when defining the dimensions for an existing measures, in this case, the variables to be analyzed are chosen by the initial researcher, through the process of review of literature, of the past literature, and we try to pick up the variables by synthesizing the literature and justifying the variables why we picked up by proper citations, and not the person conducting the analysis. It is the researcher who will do the review and try to pick up the respective variable of that respective dimensions. So factor analysis is performed on a predetermined set of items and scales. The results of factor analysis may not always be satisfactory because of the intercorrelations and the emerged dimensions. So it has to be supported logically by proper literature evidence. The items or scales may be poor indicators of the construct or construct sometimes, so we have to be very cautious about it. And there may be too few items or scales to represent each underlying dimensions. And you need to, if you have thoroughly did the literature review and you are comprehensively, adequately picked up the respective variables on the underlying, the dimensions, then it will not be a problem. Okay. Next one is the selecting the items or scales to be included in a measure. If you look at selecting the items or scales to be included in a measure, factor analysis may be conducted to determine what items or scales should be included and excluded from a measure by looking at the extraction values and also by the factor loading score of the respective variable. So similarly, if you look at the results of the analysis should not be used alone in making decisions of inclusions or exclusion. Decisions should be taken in conjunction with the theory, and there should be a lot of supportive theory evidences whenever you consider factor analysis. Whenever you do factor analysis, it should be supported by both analysis. One is exploratory factor analysis and also confirmatory factor analysis. Normally, exploratory factor analysis is done by the software called SPSS, Statistical Package for Social Science, and the confirmatory factor analysis can be done using analysis of movement of structure called, we call it as MOS software. You can download and do the confirmatory. But this session only talks about exploratory factor analysis. So decisions should be taken in conjunction with the theory. That is very, very important. That should be always cited evidence about this construct developed using exploratory factor analysis. So let us look at the steps in factor analysis. There are 4 steps we are using it in order to execute factor analysis from the data set. Factor analysis usually proceeds in 4 steps. The first step, we call it as the correlation matrix of all variables should be computed, and the second step is factor extraction. The third step, we call it as factor rotation, and the fourth step, make final decisions about the number of underlying factors. So let us deal in detail about the first step called correlation matrix. So what happened in correlation matrix? We try to generate a correlation matrix for all the variables involved in factor analysis, which is subject to data reduction. So once we identify the variables which is not related to other variables, if you find the variable is not correlated, and that variable is called a redundant variable. So that is we can check the redundant variable in by doing correlation, by looking at the correlation matrix. Any value below 0.3 is considered to be which is having a poor correlation. Any value which is having 0.90 above, which is seems to be having higher correlation, it means that both the variables or the same variable, there is no difference between them. So too much of correlation and very poor correlation will not be encouraged in factor analysis, especially in the first step called correlation matrix. If the correlation between variables are small, it is unlikely that they share common factors. Variables must be related to each other for factor model to be appropriate. So, and also as a researcher, you have to think of correlation in absolute value. So if you look at the correlation coefficient, definitely a correlation coefficient should be greater than 0.3 in absolute value, which seems to be an indicative of acceptable correlation level, and that has to be checked when you do correlation. And any variable is not meeting the requirement of 0.3 and above can be excluded from the factor analysis, and it can be very well examined visually through the appropriateness of the factor model. And moving further, the most important aspect in the first step is the Barter test of sphericity. In this test, what happens here? It is used to test the hypothesis. The correlation matrix is the identity matrix. Hope in matrix you would have studied about the identity matrix 1001. So it means that and the next explanation, what I would like to tell you is that if the value of the test statistics of sphericity is large and the associated significance level is small, it is unlikely that the population correlation matrix is an identity matrix. Whenever you reach the identity matrix by looking at the correlation matrix, then only you can execute factor analysis. Otherwise you cannot execute factor analysis. So you have to do a checkup before on the data before you execute factor analysis. And the meaning of it, if the hypothesis that the population correlation matrix is an identity cannot be rejected because the observed significance level is large, the use of factor model should be reconsidered. That's the meaning of it. And moving further, we have one more test called the Kaiser-Meyer-Olkin test, which is called KMO measure of sampling adequacy. So it talks about is an index for comparing the magnitude of the observed correlation coefficient to the magnitude of the partial correlation coefficient. Okay, so the closer the KMO measure to 1 indicate a sizable sampling adequacy. I mean the adequate sampling is there in order to execute factor analysis or not. This can be done using this test. I think an acceptable value of 0.8 and higher are great, and 0.7 is always acceptable, and 0.6 is mediocre, and less than 0.5 is unacceptable. In that context, you cannot execute factor analysis. And it is reasonably large values are needed for a good factor analysis. Small KMO values indicate that a factor analysis of the variables may not be a good idea. So next one is these two tests will give you a green signal whether to go for factor analysis or not by scrutinizing the data what we have used for factor analysis. And the second step of factor extraction. The primary objective of this stage is to determine the factor. So how many factors has been extracted, I mean emerged by having intercorrelation between the variables. So the initial decisions can be made here about the number of factors underlying a set of measured variables. For example, estimates of initial factors are obtained using principal component analysis. The principal component analysis is the most commonly used extraction method. So when you look at this, estimates of initial factor are obtained using principal component analysis. The principal component analysis is the most commonly used extraction method. Other factor extraction method include maximum likelihood method, principal accessing factor method, alpha method, unweighted least square method, and generalized least squared method, and image factoring. And normally we use principal component analysis, and the detailed explanation you can Google and explore it. And an explanation is actually beyond our scope of this subject. And please, if you are really interested, you can key in this particular methods in Google, and we'll try to understand better about all these methods in detail, and that gives you a fundamental clarity why we need to apply this particular method. And the next one is in the principal component analysis, the linear combination of the observed variables are formed. The first principal component is a combination that accounts for the largest amount of variance in the sample, that is first extracted factors. And the second principal component accounts for the next largest amount of variance, and it is uncorrelated with the first factor, the second extracted factor. Like that, a successive component explains progressively smaller portions of the total sample variance, and all are uncorrelated with each other. If you look at these, pictorial depictions, you can understand in a better sense that to decide on how many factors we need to represent the data, we use statistical criteria. You can see here the initial eigenvalue and the scree plot. So if you look at the initial eigenvalue, the determination of the number of factors, the dimension, usually done by considering only factors with eigenvalue greater than 1. And I can show you here, you can see the eigenvalue, and only 1, 2, 3, that is 1, 2, 3 is having eigenvalue, which is, you can see here, which is greater. The other 4, 5, 6, 7, 8, 9, 10 are not having a great eigenvalue. But these three dimensions are having eigenvalue. So we can conclude here that we have three factors have emerged by looking at the variance and the eigenvalue. Factors with the variance less than 1 are no better than the single variable, since each variable is expected to have a variance of 1. So very well, by looking at this output from the SPSS, we can conclude that we got how many variables, how many factors we got. 3 factors got extracted. Are you clear about it? And the next one is, and also there is one more facility in SPSS, that is, we have a scree plot. By looking at the scree plot, you look at this eigenvalue. So we put a straight line somewhere here, straight line. So above that we have 3 factors has been extracted. So from looking at this scree plot, from the component, the factors, we can conclude that there are 3 factors getting extracted. Are you clear about it? So the steep slope shows larger factor. The gradual trailing of scree shows the rest of the factor usually lower than an eigenvalue of 1. You can see here, you can draw a line straight, and you can see above the line you got 3 factors has been emerged and extracted. In choosing the number of factors in addition to the statistical criteria, one should make initial decisions based on conceptual and theoretical grounds. At this stage, the decision about the number of factors is not final, but by looking at the variance, we can compare and conclude we got more, how much extracted factor it has been emerged. But we normally use rotated component matrix. We don't, infer from component matrix using principal component. And the third step is called factor rotation. In this step, factors are rotated. So unrotated factors are typically not very good in getting an interpretation, since most of the factors are correlated with many variables. That's why factors are rotated to make more meaningful and easier to interpret. Each variable is associated with a minimal number of factors, and different rotations methods may result in the identification of somewhat different factors. Clear? And the most popular rotational method, we call it as Varimax rotation, and we need to use those methods. Varimax use orthogonal rotation yielding uncorrelated factors and components. Varimax attempts to minimize the number of variables that have high loading on a factor. This enhances the interpretability of those factors. So the other common rotational methods used include oblique rotation, which yield correlated factors. Oblique rotation are less frequently used because the results are more difficult to summarize. Let's also a little bit get an idea about the other rotational methods, which is Quartimax, that is orthogonal, Equimax orthogonal, and Promax oblique rotation. So you can see the rotated, from this you can emerge, we can infer what is a factor is interpreted or named by examining the largest value linking the factor to the measured variable in the rotated factor matrix. When you look at this first item or the variable, we can see from which factor it got loaded. So it is 0.803. So it got loaded in this first factor. And if you look at the loading, 0.186 and 0.6, so it got a poor loading. So the first variable got loaded in this first factor. And similarly, when you look at, I tried to develop a step-by-step plan of action to remedy the problem. So we can see there, this particular variable got loaded in the third factor since it is having a value of 0.694 compared to the factor 1 and factor 2, which is lesser compared to 0.694 score. So similarly, I can give you one more example, like I expressed my emotions to my family and close friends. If you look at that, it is 0.706. Obviously, this particular variable got loaded in factor 1. And if you look at this, it is 0.633 and 0.145. So it got a poor loading compared to, this particular variable called, I express my emotions to my family, and it got loaded in factor 1 and it is poorly loaded in factor 2 and 3. And we can conclude that this variable belongs to factor 1. And I attended workshops or sought some other educational approach to correct the problem. It got loaded in factor 2. It is 0.633. I tried to be emotionally honest with myself about the problems. You can see it got loaded in factor 2. And I sought advice from others on how I should solve the problem. You can see it got loaded in factor 1. And I explored the emotion caused by the problem. You can see that in this particular variable got loaded in factor 2. And also I took direct actions to try to correct the problem. You can see it got loaded in 0.772 and it got loaded in factor 3. And I told someone I could trust about how I felt about the problem. It got loaded in I think it is certainly loaded in factor 1. And similarly, when I put aside other activities so that I could work to solve the problem, it got loaded in 0.657. Like that, we can extract what are the variables which has been loaded in factor 1, 2, 3, and we can compile that into respective and we can report the results. So the fourth step is making final decisions. When you look at the final decisions about the number of factors to choose, is the number of factors for the rotated solution that is most interpretable. To identify the factors, group variables that have large loading for the same factor. Plots of loading provide a visual for variable clusters. Interpret factors according to the meaning of the variable, and the decision should be guided by prior conceptual belief about the number of factors from the past research or theory. That is, you should have a theory backup. Eigenvalue computed in step 2 and the relative interpretability of rotated solution computed in step 3. So the assumption underlying factor analysis include the measured variable or linearly related to the factor plus errors. This assumption is likely to be violated if items limited response scales, 2-point response scales, likely true, false, right, wrong items. The data should have a bivariate normal distribution for each pair of variables. Observations are independent, and the factor analysis model assumes that the variables are determined by common factors and unique factors. All unique factors are assumed to be uncorrelated with each other and with the common factors. So I think I have given an all kind of conceptual explanation about factor analysis. It's now time how you can analyze using SPSS software. The first step in factor analysis, you go to analyze and press this, hit this button called data reduction button, and you have factor analysis here. You can see here factor analysis here. Then analyze and select dimension, factor analysis box, click that. And next one, what you can do here, whatever the variables you want to put those variables into variables, and hit descriptive statistics. And once if you put these variables in that particular box, then you select extraction method. You can press this extraction. You can hit this extraction button here. Once you press this extraction button, what you can do here is you click unrotated factor solution and street plot, as I was explaining that, and also based on each value above 1, you take that. So keep all the default selections as per the SPSS, and try to hit the continue button. Once you can press the continue button, you will ask to go for what kind of rotation. You can select this Varimax rotation here. You can press this Varimax rotation here, and during the factor rotation, decide on the number of factors based on factor extraction phase, and enter the desired number of factors by choosing fixed number of factors and entering the desired number of factors or extract. Otherwise, you don't want to go for fixed number of factors. Under rotation, choose Varimax, press continue, then hit OK button. So once you did it, you will get the output. I've shown you the output in my session and explained you how to interpret that. So hope with this input, hope all of you understand what is how to do factor analysis. I think it gives you a clear picture, and also how to employ, how to execute factor analysis using SPSS, using this demonstrative input. I think you will be very clear to how to do factor analysis. Hope you will download SPSS software student version and keep some data set and try to explore and learn through self-learning. Okay. Now let's talk about how to write interpretation using exploratory factor analysis for occupational citizenship behavior of an employee. I got a data with me, I have analyzed, and I have taken an output, and for which, step by step, I am going to show you how to write interpretation for the output taken using SPSS software. We all know that statistical package for social science. We got the first table called KMO and Barter test of OCB, occupational citizenship behavior. So in that, if you look at the Kaiser-Meyer-Olkin measure of sampling adequacy, which I already explained to you, so that determines the adequate sample, I mean the sufficient sample is there in order to execute EFA, exploratory factor analysis. And when you look at the Barter test of sphericity, and if you look at the significance level, which is lesser than the lesser value, we have significance value. It means that the matrix basically has attained the identity. So this has been explained, I mean identity matrix, correlation matrix where we have attained. So this is the explanation I have given here. I will read and explain you parallelly. So Barter test of sphericity indicates whether the correlation matrix is an identity matrix or not. And if you look at that, yes, it is significant. Yes, it is an identity matrix. We can conclude, which would indicate that the variables are unrelated. The significant level gives the results of the test very small values. For example, which is lesser than 0.05, indicate that there are probably significant relationship among the organization citizenship behavior variables of the I mean the faculties in an university, because this is a study has been done in an university. I mean we have taken the inputs from the faculty of that particular university. A value higher than about 0.10 or so may indicate that this data are not suitable for factor analysis. Hence, the researcher concludes the data is suitable for factor analysis since Kaiser-Meyer-Olkin measure of sampling adequacy value is 0.548, which is more than sufficient to execute exploratory factor analysis. And we have the second output table is called commonalities. This is by looking at this commonalities, which actually indicate the amount of variance in each variable that is accounted for. Initial commonalities are estimates of the variance in each variable accounted for by all components or factors. These values are the proportion for correlation analysis or the amount for covariance analysis of variance accounted for in each variable by the rest of the variable. So that's the inference we're supposed to write under this table, I mean the output. And next one is if you look at table number 3, total variance explained. So when you look at the total variance explained, you can see here like how many variables has been got emerged. When you look at that, you have to check whether the initial eigenvalue is more than 1. So we got 4 components which got initial value above 1. So the rest of the variable from starting from 5, 6, 7, which is not more than eigenvalue of 1. So we can conclude from this inference that we have extracted 4 factors or components. And similarly, we can see the percentage. Each factor is accounted for how much of percentage, like 25 point. So the first factor, how much of variance of, percentage of variance we accounted for. And the last column talks about the, what you call the cumulative variance of each factors. So this has to be, written as an interpretation below this table. The above table gives eigenvalue, the variance explained, and cumulative variance explained for the factor solution. The first panel gives values based on initial eigenvalue. For the initial value solution, there are as many factors as there are variables. The total column gives the amount of variance in the observed variables accounted for by each factor. The percentage of variant column gives the percent of variance accounted for by each specific factor related to total variance, in all the variables. And similarly, the cumulative percentage column gives the percentage of variance accounted for by all factors up to and including the current one. For instance, the cumulative percentage for the second factor is the sum of the percentage of the variance for the first and second factor. In the above table, there are few factors that explains lot of variance, which is a sign of good factor analysis, and the rest of the factor explain relatively small amounts of variance. So I can say that, if you look at, there is 65.157% of variance has been captured by the variables we have used. I mean, these four factors capture a percentage of variance of 65%, that we can conclude. And the extraction sum of square loading groups gives information regarding the extracted factors or components in the rotation sum of squared loadings group. The variance accounted for by rotating factors or components may be different from those reported for the extraction, but the cumulative percentage of the set of factors or component will always be same. So if you look at the rotated component matrix, you can see the rotated component matrix. So the first variable, as we explained, I help colleagues who have been absent from work. So all these, I help colleagues who have heavy workload. I am mindful of how behavior affects other variables' job. So all these have been loaded in the first factor, and a variable I go out way to help new employees got loaded in the second variable, and I adhere to informal rules revised to main order. It got loaded in the second variable, and similarly, I perform duties that are not required but which improve corporate image, which got loaded in the second factor. And when you look at the third factor loading, you got my attendance at work is above the norm. It got loaded in the third factor. I take undeserved breaks at work. It got loaded in the third factor. And similarly, I often complain insignificant things at work, that got loaded in the third factor. And I tend to make mountains out of molehills. That is also got loaded in the third factor. And similarly, we got two factors got loaded in the fourth factor. That is, I take personal interest in my colleague's job, and I attend meetings that are not mandatory but considered important. So these are the two variables got loaded in factor 4. That's the conclusion. And we suppose to the above table. So how do you write the interpretation for the above table? What you have to write here, let me read out. The above table reports the factor loading for each variable on the factors after rotation. For example, each number represents the partial correlation between the items, that is faculty's colleagues who have been absent from work, which got a loading value of 0.831, and the rotated factor, it got loaded in factor 1. These correlations can help researchers to formulate an interpretation of the factors. This is done by looking for a common thread among the variables that have large loading for a particular factor. So this exercise can be well depicted in this table. You can see that you can draw a table: factors, loaded variable, factor loading values, and percentage of variance. So what you do here is you pull out all the variables which got loaded in the factor 1 and put it here. So we try to put it here, and we put that here, and go to the variance table and check the respective variance. How much? 25.121. So you try to put that one here. So how much variance these three variables comprises of is that 25.12% of variance. It is accounted by these three variables, and these three variables constitute the factor 1. So any factor name has to be given by looking at those variables which has a higher loading. So we have helping attitude and self-realization. We try to look at the commonality among these variables, and we try to coin a factor name uh, by picking up the factor which has the most loading among the variables. That has to be considered in naming the factors. So by this, through this way, we need to really, depict and write interpretation for factor analysis. And also similarly, we got factor 2, volunteering and commitment. We are given a name. And there are 3 variables got loaded in factor 2, and you can see the respective loading here. You can see factor loading values we have plucked out from there and put it here. And also in the variance table, we have taken the respective variance of factor 2 and put it here. So similarly, we have factor 3, we have named involvement, and we have 4 factors has got loaded in the variables with the respective factors, and the respective values has to be posted here. And similarly, we pluck out the variance, respective variance, and we put it here. And factor 4 also, we have 2 variables, and the respective variable loading has been taken, posted here, and the respective variance has to be mentioned here. It is 10.626. That's the way we have to clearly do a presentation of the outputs whenever we do presentation. And we conclude the above tables by writing this statement. I can read out this. The above table reflects the factors and the respective variable loadings. The percentage of variance column gives the percentage of variance accorded for by each specific factor relative to the total variance in all the variables, through which the researcher can prioritize the significance of each factor. That is, the factor with the higher variance stands prominent, followed by the next highest variance value. With this, I think I have honestly given you an overview about how to write interpretation for the output. So we got 4 tables. When you do factor analysis, we log into the SPSS software, and we hit if you follow my instructions how to hit the respective button. You got the first table called KMO Barter Test of OBs, organization citizenship behavior. Table 2 showing commonalities, and we have the third table, which is showing the total variance explained. From there we can look at the initial EGN value, and we can extract how many factors got loaded. At the same time, the percentage of variance of this respective each factor can be identified, and we can by looking at this, we can also prioritize the factors. We can conclude that the first factor having more variance, so we need to give due importance to the first factor. That is the very important synthesis we have to write it in during our findings. And we have the next table, which is called rotated component matrix. The respective variables which has got loaded into the respective factors has been depicted here. And from those 3 tables, we can draw a table like this. We can put 4 columns. Column number 1, we have factors. Column number 2, we have loaded variables. And column number 3, we have factor loading values and the percentage of variance of the factor. So it gives you a clear presentation in your report, research report, and the reader can able to understand the context, what for you are using exploratory factor analysis. We all know that exploratory factor analysis is an data reduction technique whereby many number of variables can be deducted into a small number of factors or dimensions which make the job of the presenter easy. So I think hope you all clearly understand about what is exploratory factor analysis. Hello, in continuation of our session, multivariate analysis. Let's also discuss about multiple linear regression analysis and how it is applied in the business context. Let us also give you some examples. So before that, let us understand what is multiple linear regression analysis is all about. So it is a multivariate technique, is one of the multivariate technique, we all know that. So multiple regression analysis is a statistical method for estimating the relationship between dependent variable and two or more independent variables. We have simple regression analysis and also multiple regression analysis is available. You can see the formula here. It is y is equal to a plus b1 x1 b2 x2. It is the coefficient value of each variables we are trying to predict. Using these variables, we are trying to predict the predictor variable. So this is called a dependent variable, and this one, and this one is called a three independent variable. And it goes on how many variables we have. We have to write this regression equation. So this is the regression equation. Okay. So these variables are called predictor variables, and this one a is constant and y is called dependent variable. Are you clear about it? These are independent variables. So moving further, multiple linear regression. So simply, multiple linear regression is a method for studying the relationship between a dependent variable and two or more independent variables. So the purpose we talk about is one is for the purpose of predicting things, and the other one is for explanation. The other one is for theory building. Okay, that's why we use multiple regression analysis. And I will give you a context in business. For example, when you want to really evaluate, the employee motivation level. So the motivation of the employee become a dependent variable, and the other independent variables are like reward system, non-monetary rewards, workers' relationship, working environment, like that. There are many independent variables which really trying to predict the motivation, overall motivation of the employee. Here in this context of this example, the overall motivation of the employee becomes the dependent variable, and the independent variable, just now I was mentioning about the salary, I mean the monetary reward, and the other non-monetary reward like transportation, children education, other perks. All this comes under other independent variable. And also the workers and manager and boss relationship and the working environment, all these become an independent variable which is trying to predict the dependent variable. Using multiple linear regression analysis, by looking at the coefficient value of each variable, we can predict how much of this variance is being using this coefficient value, we can predict how much this particular independent variable is trying to estimate the dependent variable, what you called in this situation as overall motivation level of the employee. So that's where multiple linear regression analysis is giving you a prediction, and also it gives an explanation how much and on which variable as a manager has to give due importance so that it will really motivates the individual employee. And also it gives you a theory building that these are the variables which constitute the holistic model for motivation in an organization. So thus multiple linear regression analysis helps the researcher for the purpose of theory building also. So let us move further to elaborate on multiple linear regression analysis. Here in the operation aspects of multiple regression analysis, there are uses the ordinary least square solution as dash simple linear or bivariable regressions, which describes a line for which the sum of square differences between the predicted and the actual values of the dependent variable are at a minimum. And also it represents the functions that minimize the sum of the squared errors. For example, if you look at here, y is the predicted dependent variable, and the other one is the constant variable, and these are the variables which is called the independent variable. These independent variables are helping us to predict the constant variable, the dependent variable called y. So next one is this multiple linear regression produces a model that identifies the best weighted combination of independent variable to predict the dependent, otherwise we call it as criterion variable. So basically here multiple linear regression analysis estimate the relative importance of several hypothesis predictors, and multiple linear regression analysis assess the contribution of the combined variables to change the dependent variable. So next one is like the design requirement of multiple linear regression analysis. So it should have certainly one dependent variable, otherwise we call it as criterion variable, and it should also have two or more independent variables, otherwise we call it as predictor or explanatory variable. And multiple linear regression analysis should have a large sample size, more than 50 samples, at least 10 times as many cases as independent variable. These are the criteria, the design requirement of multiple linear regression analysis. So the basic assumption of multiple linear regression analysis is that the independence, the data of any particular subject are independent of the data of all other subjects. And also, we need to check the normality of the data using, SPSS. You can check the normality of the data. In the population, the data on the dependent variable are normally distributed for each of the possible combinations of the level of X variables. If the data is normally distributed, then we can go for multiple linear regression analysis. Each of the variables should be normally distributed. That's the basic criteria of executing multiple linear regression analysis. And when the next one is homogeneity in the population, the variance of the dependent variable for each of the possible combination of the levels of X variables are equal. And the next, assumption is that, basic assumption is that the variables should be linearly interrelated. I mean that in the population, the relation between the dependent variable and the independent variable is linear when all other independent variables are held constant. So I think when we are trying to use multiple linear regression model, this data has to abide by this basic assumption. We need to check on that. And when you talk about the differences between a simple versus multiple regression analysis, it is quite obvious fact that In simple regression analysis, we have only one dependent variable and predicted from one independent variable. I need to stress on that one independent variable, because in simple regression analysis, we are using only one dependent variable and one independent variable. Whereas in multiple regression analysis, we are using one dependent variable, but it has been predicted by multiple independent variable like x1, x2, and etc. Do you understand this? And the next one is, let's talk about the, here we get only one regression coefficient, but here for each independent variable, we will get each regression coefficient value associated with that specific independent variable. And next one is here R square. When you talk about R square, the proportion of variance in dependent variable y predictable from x, whereas in multiple regression analysis, the proportion of variance in dependent variable y predictable by set of independent variables. So that is very, very important as far as the multiple regression is concerned. So hope with these features, we can distinguish the differences between simple and multiple regression analysis. Next one is, let us move further to understand the equation aspects of multiple linear regression equation. So I can show you here, this is called the dependent variable, this is a constant factor, and this one is independent variable, and the next independent variable, and just like that it is followed on. So y is the dependent variable and x is the independent predicted variable, and this dependent variable is predicted by the independent variable. The respective coefficient value will determine how much the dependent variable has been predicted by this each independent variable, and A is nothing but the raw score equation, which includes a constant or y. It means that intercept OB y axis representing the value of y when x is equal to 0. So B is equal to weight or partial regression coefficient, and x1 is considered to be the independent variable. The BS shows the relative contribution of the independent variable on the dependent variable when controlling for the effects of the other predicted. Regression linear model building. So what happens here? Each predictor is taken in turn, that is, all other predictors are first placed in the equation, and then the predictor of the interest is entered. This allows us to determine the unique contributions. So this allows us to determine the unique contribution of the predictor variable. By repeating the procedure for each predictor, we can determine the unique contribution of each independent variable. This thus it facilitates the model building exercise using these variables on the dependent variable. Next one, different ways of building regression models. So one is, there are many models. I think enter method or simultaneous method, all independent variables entered together, that we call it as enter method. And the stepwise method, our independent variables entered according to some order. So in SPSS, automatically it has been put in order by size or correlation with the independent variable in order of significance. And also we have a hierarchical independent variable entered in stages. So these are the three methods, but we are going to talk about the simultaneous method. We call it as enter method, since all independent variables are entered simultaneously into the talk about this. Let's move on to using this one. So if you open up the multiple regression analysis using the SPSS, you need to go to analyze, and you have to from analyze you need to go to regression, and regression to linear. So once you move it, then what happens? You get a box like this. You put that dependent variable, whatever the dependent variable, you try to put it here, And the next one is you try to put this independent variable over here, and just it is by default we have enter method here, and don't press any other statistics, and everything is okay. Just hit the OK button. So what happen, if you press the statistics, you will have a open up box like this. By default it will be here. So just give you continue, because use probability of f 0.0 already default. By default it is given 0.05, and include constant in equation, so that is always there. Click. So by default exclude cases listwise, continue button. Then what happen, you get an output like this. So this is called R and R square and adjusted R square. So when you run regression analysis on SPSS, you get three tables. Each tells you something about relationship. The first is the model summary. The R is the Pearson product movement correlation coefficient. In this case, R is 0.736. R is the square root of R squared, and is the correlation between observed and predicted values of the dependent variable, which I was explaining you. And next one is when you talk about the R, talk about the model fit, and it's okay. 0.736, it's okay. And R square talks about the relationship between the dependent variable and independent variable. And the error value R square is the proportion of variance in the dependent variable, in this case income per capita, which can be predicted from independent variable level of education. The value indicate that 54.2% of the variance in income can be predicted from the variable education. So this is with the simple linear regression. R square is also called the coefficient of determination. So we have to, this R square value is very important in writing inferences using multiple regression analysis. And next one is we talk about adjusted R square. The adjusted R square attempt to yield a more honest value to estimate R squared for the population. The value of R square was 0.542, while the value of adjusted R square is 0.532. There is not much difference because we are dealing with only one variable. And the number of observation, the independent variable, is small, and the number of predictors is large. In that case, I think there will be much greater difference between R square and adjusted R square. Next one is the second table we receive out of SPSS analysis is called this ANOVA table. If the p-value is greater than 0.05, it means that you would say that the group of independent variables does not statistically significant relationship with the dependent variable. But in this case, it is lesser than 0.05, and we can conclude that yes, there is a statistical relationship between independent variable and dependent variable, so that the group of independent variable does not reliably predict the dependent variable in this case. Next one is the regression coefficient. You can look at the regression coefficient. So you can have this beta value, okay, and it is it is called the standardized coefficient value, beta. These are the coefficients that you would obtain if you standardize all the variables in the regression, including the dependent and all of the independent variable, and you can run the regression test. So if you run that, what happens, you can see that how much 73.6% it is having a relationship, it is having a variance with that of the dependent variable. So by standardizing the variable before running the regression, you have to put all of the variables on the same scale, and you can compare the magnitude of the coefficient to see which one has more of an effect on the dependent variable. So this is a very good statistical tool whereby we can really predict the value of each independent variable and how much it is significant or important as far as in predicting the dependent variable. So in many business contexts, I think we can run this multiple regression analysis to predict the latent dependent variable. So you will also notice that larger betas are associated with larger t values. That's the thing. So you can see that it is so significant. So we have a larger t value. So next one is the SPSS output. I already showed you. This is the first table, second table, and if you have a multiple variable like this, you go to this significant table, and you can see this only this particular variable is significant. So here, weight of the dependent variables is days in the hospital. In case of our discussion of Vignet Hospital, and the weight of the subject is very, very important, and this is very, very significant when you go for this treatment of the patient. So weight of the subject, this is significant. Why it is significant? Because of the fact that this value is lesser than 0.05, and if you look and notice that the t value is also looking to be very high, that is 2.357. So that's where, if any of the variable is significant, no, I don't think no value is observed to be lesser than 0.05. So we cannot, infer that any of the significant variables other than weight of the subject is available in this table. So with that, I think to recap, we start with multiple regression analysis. Then we start with factor analysis, and then we also demonstrated using SPSS, and also we start with the fundamental understanding of multiple regression analysis and simple regression analysis, and which context we will be using this simple and multiple regression analysis, and hope these two multivariate technique will be very, very useful for you in your business research process. Wherever there is a practical situation demands, you can employ these two techniques to understand which are the independent variable is trying to predict the dependent variable, and you can also reduce the number of variables into minimum using exploratory factor analysis. I mean, you can reduce into minimum factors, okay, using factor analysis, and you can build a theory using these two multivariate technique. Hope you guys have understood clearly and get fundamental clarity on these two statistical technique. One is factor analysis, we call it as EFA, exploratory factor analysis, and the next one is multiple linear regression analysis. Hope you guys enjoyed the session. Thank you so much.